one thing that I didn't talk about is the photoelectric effect. So we'll discuss that briefly now. It turns out that it was discovered quite some time ago, and as a matter of fact, Albert Einstein won the Nobel Prize, I believe it was in 1919, for his work on this particular phenomenon known as the photoelectric effect. A lot of people think that Einstein was awarded the Nobel Prize for his work on relativity. That's not true, but he did receive the Nobel Prize for his work on the photoelectric effect. Now, what is the photoelectric effect? Fundamentally, what it is if I take a metal, and it could be something like the metal sodium, it could be almost any metal we could use, and I shine a light on the surface of that metal. So here's the metal, and here are photons, what we would call particles of light that are beaming down onto the surface. When the photon hits the surface, depending on what its color is, which is really determining what its energy is going to be, depending on the color of the light, it's going to have a sufficient energy in order to be able to actually interact with the surface of the sodium and eject one of the electrons. That is to ionize, that is to go from E1 to E infinity, to actually be able to eject that electron, to cause that electron to move off of the surface. Now with gases, we have to put a lot of energy into doing that. So shining a light is not going to work. But with metals, the electrons are more loosely bound, and we can find, for any given metal, we can find usually some particular wavelength of light that is sufficiently energetic that a single photon reacting with the surface will eject a single photoelectron. So here's our photoelectron being ejected off of the surface. Now, it doesn't matter how many photoelectrons fall on this surface. If they don't have the appropriate energy, how many photons fall on the surface, they are not going to eject even a single photoelectron. But a single photon with the correct energy, it could be greater than that threshold energy, will actually eject a photoelectron. So that's what the photoelectric effect is all about. And you can see that, you can actually have that illustrated if you use what are called photocells, for instance. They're actual cells when you, something called a photodiode, when you actually shine light on it, it will actually eject photoelectrons and will produce a current, and you can use that current to do something. So they used to have, for instance, electronic devices like doors and things that would open when a light beam was shown across them, or if you broke the light beam, that would create some kind of a current. So either the light beam being on would stop something from happening, and when you broke it, then it would actually happen. So that you have automatic doors that operate in that particular fashion. Okay, so all electronic transitions are quantized. I mentioned that already. I don't think I mentioned this, though, that the energy of any given photon is equal to this quantity, which is a constant called Planck's constant. And it's equal to 6.6. I never remember the values of these things. I think it's 6.673. I'll look that up in your book. Times 10 to the minus 34th joule seconds. So joule is a unit of energy, which is equal to a Newton meter, which is a kilogram meter squared per second squared. And so you're multiplying that by seconds. So the unit would actually be kilogram meter squared per second. That would give you the units of Planck's constant. And you're going to multiply that by the frequency, or I prefer to use nu, but it doesn't really matter. Your book is using F, so let's use F. So the energy is equal to Planck's constant times the frequency of the light. If we want to do this with wavelength of light, we know that the speed of light, or the speed of any electromagnetic, or this actually works for any velocity. Velocity is going to be equal to frequency times wavelength. Wavelength is going to have the units. Let me write it the other way around. Let's say wavelength times frequency. So wavelength will have the units, let's say, of meters, and frequency will be in reciprocal seconds. That's 1 over second. So if you multiply 1 meter times 1 reciprocal second, you get 1 meter per second. And that distance divided by time is a unit of velocity. So that's velocity. We say that c is also equal to lambda times the frequency. So now we have a way of actually relating frequency and wavelength using the speed of light. And if I want to put my equation in terms of lambda, I can then solve for frequency. Frequency is equal to c divided by lambda, and then substitute that value in here. So I can say that it's hf, and that is also going to be equal to hc divided by lambda. So you can see that energy is inversely proportional to wavelength, and it's directly proportional to frequency. That is to say, the greater the frequency, the greater the energy, the greater the wavelength, the smaller the energy. So again, to get greater energy, we need a smaller wavelength light. So we would prefer not to use something like, say, in the red region of the spectrum, but we might want to go back down to the green, or the violet, or the blue, or the violet region of the spectrum. And I actually do have a demonstration, but again, you're not going to be able to see it, which is very, very neat. Similar to the photoelectric effect, but if I shine a laser on a board that is impregnated with a particular chemical that glows when it's exposed to certain wavelengths of light, I have a blue laser, I have a red laser, a green laser, and a violet laser. And the shorter the wavelength, the brighter this board will glow. It doesn't glow at all when I shine even a very, very powerful red laser against it. When I shine a green laser, it doesn't glow. But if I take my violet laser, even a fairly weak violet laser, and shine it against the board, I'll actually see, I can actually write on the board, and it will glow for some period of time after I've stopped writing on it. Okay, so talked about everything except what I think is going to be our very, very last topic of discussion, and that is spectral line analysis. And this, again, is a very, very important topic. And so we've seen what causes spectral lines to form, and what kind of information can we get from a line spectrum. Well, one of the things that I've told you already that you can do with it is, because every element has a particular and distinctive line spectrum, you can actually look at light that's coming from a distant star and determine what the chemical composition of the atmosphere of that star happens to be. That is, we can actually look and see what kind of a star we're dealing with. We can see the hydrogen and the helium, and anything that, beyond that that happens to be charged up in the atmosphere, whether we've gone to carbon or even all the way to iron, we'd actually be able to see those elements present in the line spectrum. The other thing that we can get from spectral line analysis, looking at Doppler shifts, is as I mentioned before when we were discussing the Doppler effect, is that we can calculate and find the radial recessive speed. So what we can do is we can actually use a formula where we can say the radial speed or radial velocity, which I'm going to call V sub r. So I'm assuming that this is a star, and the star is moving. I'm looking right at the star, and the star is moving directly along my line of sight. It's either moving towards me, or it's moving, let's say it's moving away from me in this particular instance. But it could be something that's moving towards me as well. That's going to be equal to the change in wavelength, which I'll call delta lambda, This is the change in wavelength. Divided by the unshifted wavelength. In other words, for any particular line, the line is going to have a characteristic wavelength that's associated with it. For instance, the hydrogen alpha line, this red line is, I don't remember exactly what it is, but let's say it's somewhere around 653 nanometers. So if this got shifted, if the hydrogen alpha line got shifted, let's say to 651 nanometers, then delta lambda would be -2 nanometers. And lambda would be the unshifted wavelength, 653. And then we would multiply that by c, by the speed of light, and that would actually give us the velocity. That would actually tell us what the velocity of that particular object happened to be. And because the sign in this case would be negative, that would tell us that this was actually moving towards us. If the sign were positive, that would tell us that it was moving away from us. So we can actually use the Doppler shift for spectral line analysis to get an indication whether an object is moving towards us or away from us, and not just the fact that it's moving towards us or away from us, but how fast is it moving towards us or away from us. So that's a very, very interesting kind of thing. A couple other things. There's something having to do with line broadening. So very frequently we don't see a very sharp line, but we'll actually see a line that broadens a little bit like that. So it's not going to be, it's not a continuum, but the line is actually split out a little bit. And there's a number of reasons that this can occur. But one reason for line broadening is that individual molecules that are going to be in the atmosphere, some of those are going to be moving towards us, some of them are going to be moving away from us. So the ones that are moving away from us are going to be red shifted, and the molecules that are moving towards us are going to be blue shifted. They're going to move out this way, and so on average we know that this would be the unshifted position of the line, but because all these things are in motion, it broadens the line. It makes the line a little bit wider. So that's one thing that we get, one thing that causes line broadening. Another one is that we could be looking at a star where the star is rotating, and it could be rotating at a fairly rapid speed. Some stars rotate very, very rapidly. So when the star is moving towards us, we're actually going to see a blue shift in its light, and when it moves away from us, we're going to see a red shift. So on this side we get blue, and on this side we get red. So that's another example, this one having to do with the actual motion of the star itself rather than the individual molecules. That's also going to produce a broadening. Another thing has to do with the temperature of the star, and it turns out that hotter gases move faster, and they will have a greater Doppler shift. So we can also see a Doppler shift, an increase or a certain amount of broadening that occurs. Again, it's going to be red and blue shifted, but the hotter the gas, the greater the amount of shift that we would see. The greater amount of broadening we would see in this Doppler shifted band. That's really not a Doppler shift. Well, yes, it is. It's still considered a Doppler shift. And there's one other thing that produces line broadening. It's something called the Zeeman effect. And the Zeeman effect just has to do with the fact that in the presence of a strong magnetic field, these lines are actually split into multiple lines. So what would be an individual line is split into a number of lines, and that also causes a broadening effect. So that's a Zeeman, which is a magnetic, from magnetic field, the magnetic field causing a line broadening. And there's some objects that have very, very strong magnetic fields that would cause a very significant broadening. There are certain stars, neutron stars, for instance, that have enormous magnetic fields, and we would see a lot of Zeeman broadening from that. Okay, that concludes this chapter. And again, remember that I'm holding you responsible not for any other things in the chapter, but just for the things that I actually discussed. Again, thank you for your patience and your participation, and good luck again.